Example 14.1. What force must a dam withstand? So, consider the pressure and force acting on the dam retaining a reservoir of water on figure 14.7. Suppose the dam is 500-meter wide and the water is 80.0-meter deep at the dam, as illustrated below. So, A. What is the average pressure on the dam due to the water? B. Calculate the force exerted against the dam. So, the average pressure P due to the weight of the water is the pressure at the average depth H of 40.0 meter. Since pressure increases linearly with depth, the force exerted on the dam by the water is the average pressure times the area of a contact, which is F equals PA. So, we will come up to the solution. First, we will find the average pressure due to the weight of a fluid, which is we will use the formula P equals HPG. So entering the density of water from table 14.1 and taking H to be the average depth of 40.0 meter, we obtain P equals 40.0 meter multiplied by 10 cube kilogram per meter cube multiplied by the gravity 9.80 meter per second squared. So we will multiply the 3 and we will come up to the answer 3.92 times 10 to the power of 5 Newton per meter square is equal to 392 kPa. So, second, we have already found the value for P. The area of the dam is A equals 80.0 meter multiplied by 500 meter is equal to 4.00 times 10 to the power of 4 meter squared. So that after we find the value of the average pressure and the area of the dam, we will come up to the formula F equals PA, which is P is equal to 392 kPa multiplied by the area 4.0 times 10 to the power of 4 meters squared. So before that, we will use the 3.92 times 10 to the power of 5 n per meter squared as P and 4.0 times 10 to the power of 4 meters squared as the area. So multiplied and we will come out to the answer 1.57 times 10 to the power of 10 Newton. So therefore, nganong Newton ra ang nabilin, which is cancel na to ang m squared, then nabilin ang Newton. So multiply 4.0 times 10 to the power of 4 multiplied by 3.92 times 10 to the power of 5 will come up to the answer. Force equals 1.57 times 10 to the power of 10 Newton. So, although this force seems large, it is small compared with the 1.96 times 10 to the power of 13 Newton weight of the water in the reservoir. In fact, it is only 0.0800% of the weight. Example 14.3. Calculating force on wheel cylinders. Pascal puts on the brakes. Consider the automobile hydraulic system shown in figure 14.18. Suppose force of 100 Newton is applied to the brake pedal, which acts on the pedal cylinder acting as a master cylinder through a lever. A force of 500 Newton is exerted on the pedal cylinder. Pressure created in the pedal cylinder is transmitted to the four-wheel cylinders. The pedal cylinder has a diameter of 0.500 centimeter and each wheel cylinder has a diameter of 2.50 centimeter. Calculate the magnitude of the force F sub 2 created at each of the wheel cylinders. So, in figure 14.18, hydraulic brakes use Pascal's principle. The driver pushes the brake pedal, exerting a force that is increased by the simple lever and again by the hydraulic system. Each of the identical wheel cylinders receives the same pressure and before creates the same force output F sub 2. The circular cross-sectional areas of the pedal and wheel cylinders are represented by A sub 1 and A sub 2 respectively. We are given the force F sub 1 applied to the pedal cylinder, so the cross-sectional areas A sub 1 and A sub 2 can be calculated from their given diameters then we can use the following relationship to find the force F sub 2. So we will come up to the formula F sub 1 over F sub A sub 1 is equal to F sub 2 over A sub 2. So manipulate this algebraically to get F sub 2 on one side and substitute known values. So we will apply the Pascal's principle to hydraulic system given by F sub 1 over A sub 1 equals F sub 2 over A sub 2. Therefore, ang atong gipangita is F sub 2. So, ato siyang eliminate ang A sub 2. So, mag-come up ta sa formula F sub 2 equals A sub 2 over A sub 1 multiplied by F sub 1 is equal to pi r square over pi r square multiplied by F sub 1. So, A sub 2 is equal to open parenthesis 1.25 centimeter close parenthesis squared over 0 open parenthesis 0.250 centimeter close parenthesis squared multiplied by the force, or the F sub 1 is 500 Newton. So after we squared the A sub 2 and A sub 1, we will divide it and we will multiply to 500 Newton, which will come up to the answer 1.25 times 10 to the power of 4 Newton. So this value is the force exerted by each of the four wheel cylinders. Note that we can add as many wheel cylinders as we wish. If each has a 2.50 centimeter diameter, each will exert 1.25 times 10 to the power of 4 Newton. A simple hydraulic system, as an example of a simple machine, can increase force but cannot do more work than is done on it. Work is 4 times distance moved, and the wheel cylinder moves through a smaller distance than the pedal cylinder. Furthermore, the more wheels added, the smaller the distance each one moves. So many hydraulic systems, such as power brakes and those in bulldozers, have a motorized pump that actually does most of the work in the system. Example 14.4. Calculating average density. Suppose a 60.0 kilogram woman floats in fresh water with 97.0% of her volume submerged when her lungs are full of air. So what is her average density? We can find the woman's density by solving the equation fraction submerged, the average density over the density of the fluid. So for the density of the object, this yields the density of the object equals the density of the person is equal to fraction submerged multiplied by the density of the fluid. So we know both the fraction submerged and the density of water, so we can calculate the woman's density. So entering the known values in the expression for her density, so we obtain the density of a person is equal to 0.970 multiplied by 10 kilogram per meter cube is equal to 970 kilogram per meter cube. So the significance, or the woman's density, is less than the fluid density, so we expect this because she floats. Example 14.5. Calculating fluid speed through a nozzle. A nozzle with a diameter of 0.500 centimeter is attached to a garden hose with a radius of 0.900 centimeter. The flow rate through hose and nozzle is 0.500 liter per second. Calculate the speed of the water, A in the hose and B in the nozzle. So we solve the flow rate equation for speed and use pi r squared for the cross-sectional area of the hose, obtaining V equals Q over A, R equals to Q over pi r squared. So substituting values and using appropriate unit conversions yields. So V equals 0.500 liter per second multiplied by 10 to the power of negative 3 meter cube per liter divided by 3.14 open parenthesis 9.00 times 10 to the negative power of 3 meter close parenthesis squared. So after we multiplied the denominator and the numerator, we will divide it and we will come up to the answer 1.96 meter per second. So second, we could repeat this calculation to find the speed in the nozzle. But we use the equation of continuity to give a somewhat different insight. So the equation states a sub 1 multiplied by v sub 1 equals to a sub 2 multiplied by v sub 2. So solving for v sub 2 and substituting pi r squared for the cross-sectional area yields, we will come up to the formula v sub 2 equals a sub 1 over a sub 2 multiplied by v sub 1, so equals 1 pi r squared over pi r squared multiplied by v sub 1 is equal to r squared over r squared multiplied by v sub 1. So substituting known values, v sub 2 is equal to 0.900 centimeter squared and 0.250 centimeter squared multiplied by 1.96 meter per second. So after we square the denominator and the numerator, we will divide it and multiply to the v sub 1, which is 1.96 meter per second, and we will come up to the answer v sub 2 is equal to 25.5 meter per second. So a speed of 1.96 meter per second is about right for water emerging from a hose with no nozzle. The nozzle produces a considerably faster stream merely by constricting the flow of a narrower tube. So the solution to the last part of the example shows that speed is inversely proportional to the square of the radius of the tube, making for the large effects when radius varies. We can blow out a candle at quite a distance, for example by pursuing our lips, whereas blowing on a candle with our mouth wide open is quite ineffective. Example 14.7. Calculating pressure of fire hose nozzle. A fire hoses used in major structural fires have an inside diameter of 6.40 cm, shown in figure 14.33. Suppose such a hose carries a flow of 40.0 liter per second, starting a gauge pressure of 1.62 times 10 to the power of 6 Newton per meter square. The hose rises up 10.0 meter along a ladder to a nozzle having an inside diameter of 3.0 centimeter. What is the pressure in the nozzle? So according to figure 14.33, pressure in the nozzle of this fire hose is less than at ground level for two reasons. The water has to go uphill to get the nozzle, and speed increases in the nozzle. In spite of its lowered pressure, the water can exert a large force on anything it strikes by virtue of its kinetic energy. Pressure in the water stream becomes equal to atmospheric pressure once it emerges into the air. So we must use Bernoulli's equation to solve for the pressure, since diff is not the constant. So Bernoulli's equation is P sub 1 plus 1 half PV sub 1 square plus PGH sub 1 is equal P sub 2 plus 1 half PV sub 1 squared plus PGH sub 2. So where subscripts 1 and 2 refer to the initial conditions at ground level and the final conditions inside the nozzle, respectively. So we must find the speed v1 and v2 since q is equal to a sub 1 multiplied by v sub 1. So we get v sub 1 equals q over a sub 1. So it is equal to 40.0 times 10 to the negative power of 3 meter cube per second divided by pi 3.20 times 10 to the power of negative 2 meter close parenthesis squared. So after we squared the denominator and multiplied by pi, we will divide it to the numerator and we will come up to the formula 12.4 meter per second. So similarly, we find the V2. So V2 is equal to 56.6 meter per second. So this rather large speed is helpful in reaching the fire. Now, taking h sub 1 to be 0, we solve Bernoulli's equation for P sub 2. So we will derive to the formula P sub 2 equals P sub 1 plus 1 half P multiplied by the difference of V sub 1 squared and V sub 2 squared minus by PGH sub 2. So, substituting known values yields P sub 2 is equal to 1.62 times 10 to the power of 6 Newton per meter square plus 1 half multiplied by the 1000 kilogram per meter cube multiplied to the difference of 12.4 meter per second squared and 56.6 meter per second squared minus 1000 kilogram per meter cube multiplied by the gravity 9.80 meter per second squared and to the h sub 2 10.0 meter. So we will come up to the formula and the answer will be 0. So this value is a gauge pressure since the initial pressure was given as a gauge pressure, thus the nozzle pressure equals atmospheric pressure as it must, because the water exits into the atmosphere without changes in its conditions.